Hello, we're back talking about graphing quadratic equations, and I wanted to talk about the standard form quadratic equation a little bit. But before giving you some examples, I wanted to relate that to the vertex form of the quadratic equation that we discussed previously. And that looks something like this. A times the quantity x minus h squared plus k, and that's all equal to y. And if you recall, the vertex is located at hk. Vertex located at hk. Now the reason why I bring this up is I just want to rework this until it looks something more like the standard form quadratic equation so that I can show you how to get the vertex from that equation. I could take a derivative of this equation, but I want to do it algebraically, since most of what I talk about so far is not derivatives or any kind of calculus. So let me just expand this out. This would give me y equals a times the x minus h quantity squared component. After I square it, becomes x squared minus 2hx plus h squared. And I still have the plus k. And you can verify that for yourself. Take the steps to do it. This then becomes ax squared minus 2ahx plus ah squared plus k. And it looks a lot uglier, but it actually does look already something like my standard form quadratic equation. Notice what happens if I match that up with the standard form quadratic equation. Plus bx plus c. If I match it up, then you can see that the leading coefficient of a is the same in both equations. This guy, right, what do I want? A blue. The a is the same in both equations. But how about b? Well, it turns out that b apparently must be equal to this quantity right here, negative 2ah, and then c must be equal to all this stuff over here, ah squared plus k. Now I am eventually going somewhere with this. Let me focus on that b equal to negative 2ah. h. And if I solve for h, I can divide both sides by negative 2a, and that gives me h is equal to negative b over 2a. Or b over negative 2a, you can just pull that negative up off to the side. Now, why did I solve for h? I solved for h because the vertex from the vertex form is located at hk. So actually, I can say that the x component of the vertex related to the standard form must be located at negative b over 2a. Now you can make some thing about k here also. I can say, all right, c must be equal to ah squared plus k. And if I solve for k, this gives me k is equal to c minus ah squared. Of course, I don't want the h in there either because I'm relating it to the standard form, which doesn't have an h. So this is c minus a times h I just solved for over here, negative b over 2a, quantity squared, which equals c minus a times b squared over 4a. After I do the squaring, these a's cancel. And I can say I've got c, oh, this is a squared, by the way, so it doesn't totally cancel, c minus b squared over 4a. I still have one a down there. Now, you could do this with the k, although I should say that that's not usually how we find the y component of the vertex, which is what this is. c minus b squared over 4a, although it certainly is possible. So we'll hang on to this, and we'll hang on to this, And what that tells me, again, is that the vertex of the standard form must be the following. The vertex is located at negative b over 2a for the x component. And you could say this, you could put all this in there for the y part, c minus b squared over 4a. But as I said, practically, we don't usually do that. Usually we'll just find the x component of the vertex and then plug that number back into the equation to find the y component. But I might show you both ways just to check it out. So let's do an example then and see if we can find the vertex and go from there. I'm going to go ahead and erase my little bit of work here. You can always rewind it, of course, if you want to see that. Pause it, take a picture, print it, whatever you want to do. Okay, and then we come back with the other guy. And this kind of sort of works. Sometimes not so great, unfortunately. Adds time and space to some server somewhere keeping all this information. Wait a second, does it add space? Well, that's a consideration for you. Or is it more like a maximal level of organization? I don't know. Okay, back to the math. Here's an example that I have written down. Y equals 2x squared minus 12x plus 23. Y equals, no, what did I just say? 2x squared minus 12x plus 23. And I picked this one because it relates to one of the equations I used in a previous video. So you can compare the vertex form and graphing that to the standard form and graphing this. You just got to figure out which two equations are the same. And I'm going to use my vertex here. This is how we practically do it. If I want to find the vertex, I will look at the x value by taking negative b over 2a. So right now, b is negative 12. So this gives me negative. I got a negative 12 up here, all over 2 times a, which is 2. And then just finish this computation. Let's see, the negative and negative cancel to give me a positive. I can bag some of this. It's really 12 divided by 4, so let's just go straight to the conclusion here to say that the x value of the vertex is 3. Now typically to find the y value of the vertex, what we do is plug that value into the original equation. So I'm just going to plug the 3 in there. Y equals 2 times 3 squared minus 12 times 3 plus 23, and then we'll just keep going here. This gives me y equals 2 times 9 minus 36 plus 23. This gives me 18 minus 36 plus 23, which is negative 18 plus 23. Let's see, equals, if I added 20 to that, I would be at the positive 2. I'm adding 23, so positive 5. And what that tells me is that I can put a point on the graph at 3, 5, and I know that's either the maximum or the minimum. It's either the top or the bottom of whatever this quadratic equation turns out to look like on the graph. Now, I do need to figure out how to find the other values, or at least some other values. The nice thing about knowing where the vertex is, is it helps me choose other values for which I can find points here. So the vertex is located at 3, 5. And remember that the axis of symmetry goes right through the vertex. So what I'll do is I'll plot that point, and then I'll choose an x value, maybe a couple x values, just kind of around the x value of this vertex when I make a little table before I graph it. So let me go ahead and do that here. I'm going to try to find space for all this. I obviously took up way too much space. Here's my little baby table. X, Y, and the central point here, I'll stick 3 for the vertex, and maybe we'll go 2, 1, 4, 5 on the other side. Okay. So I'm sticking the vertex right in the middle. I already know this is 5. And the other two guys, I just got to plug in the values. If I plug in 1, then I get y equals 2 times 1 squared minus 12 times 1 plus 23, which comes out to, here, I better put that up here, 2 minus 12. I'm skipping ahead a little bit, doing this square and then multiplying it by 2, multiplying that, plus 23 equals negative 10 plus 23. Okay, and that is 13. Stick that right there. How about 2? Well, this gives me y equals 2 times 2 squared. Feel free to fast forward me if you'd like. Minus 12 times 2 plus 23 equals, I'll just bleed into this space here, 2 times 4 minus 24 plus 23 is equal to 8. I'll do this minus 24 plus 23. That works well with my mind. 8 minus 1 is 7, so I'm going to stick a 7 here. And then by symmetry, this should be a 7 and this should be a 13, but let's go ahead and verify it. So we're checking an x value of 4. 2 times 4 squared minus 12 times 4 plus 23 equals 2 times 16 minus 48 plus 23 equals 32 minus 48 plus 23. 32 minus 48 equals, what's the difference there? 16 negative. Plus 23. And 16 minus 23 gives me 7. So that one verifies this. And you know what I'll do? I'm just going to leave this 13 over there and say that, yeah, by symmetry it should be 13, and I'd like you to check it out on your own. Okay, so if I plot these points, it looks like everything we're looking at is in the first quadrant. Okay, 1 through 5 in the x. We got to at least get to 13 in the y. So maybe what I'll do here is go by 5s in the y-axis. There's 5, 10, top of the page, 15, and I'll do 1, 2, 3, 4, 5 for the x. You don't have to use the same scale for the x and the y-axis as long as you're going in well-defined steps. I don't even want to say equal, I just want to say well-defined. And in this case, we are doing equal steps of 5 for the y-axis, equal steps of 1 for the x-axis. So if x is 1, y is 13, and let's see, 1, 2, 3, 4, yeah, a little bit bigger, 1, 2, 3, 4, it's more like that, 5, so 13 is about here. And 2, 7. 1, 2, 3, 4. See how I'm breaking that up? 5, 6, 7, about there. And 3, 5 was our vertex. Okay, by symmetry, we've got these other points, 4, 7, and 5, 13. And then you connect it with as smooth of a curve as you can. And there is our graph. There's something else I could say about this. Aside from the axis of symmetry, which is this guy, which I abbreviate AOS. The vertex is right there. But I also could say, hey, I knew it was going to be going up. I knew it was going to be a smiley face and not a sad face. How come? Because originally, my leading coefficient is positive. And remember that when I did that work matching it up to the vertex form, the leading coefficients were the same. And when we looked at the vertex form, if the leading coefficient was positive, it was happy face. If it was negative, it was a sad face. So let's go on to another video, and I'll show you a couple more examples of working with the standard form quadratic equation.